Hello everybody. Today is 28 July 2023 and here's another video on the series of research in climate change. And this one is a little bit an outlier. It's called empirical forecasting, and that is because this is not specifically only for the climate change but also is applicable to other subjects. So that is why I happily invite everybody to listen to this, because maybe there's also something interesting for people that are not in the climate research. So the title is Perils and Pitfalls of Empirical Forecasting, and this is based on one of our publications with me, Peter Stallinga, and my colleague Igor Chmelinsky. It was published in the European Scientific Journal 2017. You can find it in, like always, these videos. The video itself can also be found there, or a link to it. And the paper can be found, a link to it can be found in stallinga.org. It can also be, of course, be found on that journal itself, and it can also be found by the Department of Information number or the link here below the video. Now, so let's get started. So what is this thing that is called empirical forecasting? What is it? Well, by definition, the empirical forecasting is that you use past information to make some kind of probabilistic analysis and to make some kind of probabilistic predictions of the future. So the probabilities of what events can happen in the future. And if you do it purely empirical, it means you use only the past information. So no modeling on any physics laws or any other laws. Purely empirical is only using the past information. And I will show here why this is like a poor man's tool and actually will lead to nonsensical conclusions. So to show you immediately why this is also not only applicable to the climate but also to other areas, imagine that we are predicting the stock market. And let me give you here an example. Imagine that we have here a system, let's say we have here some time series, we have as time, we have maybe the price of a stock market, PT. And maybe it was doing sort of like you measure it every day and you get a little bit noise, but it looks like it is sort of like a straight line. And now imagine that we are here, this is today, and you have to make a prediction about what is going to be tomorrow or next week is going to be the price of this stock. And I guess that everybody will say like, hey, wait a second, it goes up very nicely linearly. So probably it will go like this. That means that, hey, wait a second, here the price is maybe €1 and here maybe the price is €2. So I can get guaranteed, I can make €1 profit. But that is not how it works, because if everybody has this data, then everybody could make this prediction. And that means that everybody will say already today, say like, well, next week it will be 2. So I will offer actually 1.99 or something like this, or actually very close to 2. So that means that immediately this information is available, the price would go in the same day, would go very close to that value 2. And then there goes your profit margin. So this is what is called the efficient market hypothesis, meaning that with an open and efficient market where everybody has availability to the same information, so no inside trading, then prices are not forecastable, since otherwise anyone would be able to attain unlimited gains. Therefore, stock recommendations should be ignored by the wise investors, because they are at best self-fulfilling prophecies of the ones that are doing the predictions, and they are the ones that are getting rich, and you are the one that is getting swindled out of money. So this is already some nice introduction to show that empirical forecasting is actually not a very good tool to use for your predictions. The other end of this spectrum is what Aristotle said. He said that the only thing that will happen can happen. So if, for instance, if tomorrow it's going to rain, it is either 0% because it will not rain, or it is 100% because it will rain. There are no probabilities in this. And if you want to find out which one of the two it is, you have to do calculations based on physics laws or whatever. You can actually predict it if you are very intelligent and wise. So this is actually what we present here, is actually also the ideas repeating the ideas, working out the ideas of Aristotle to things like the climate and other such related areas. Now, to give you another example of this, how this can go wrong, and this is actually also, I presented already in the video about the psychology of anthropogenic global warming. There's another video that you can also find the link here below or in stallinga.org, and it is from the paper of us also in the European Science Journal of the year before, of 2016. That is what is called, as you can already see here, one of the pitfalls in empirical forecasting. Imagine you have a roulette table, and imagine it came out 20 times red in a row. And now we have what is called, we can have a cognitive bias. If you use that 20 times, you use that of predicting the future, you will think like, hey, wait a second. Obviously, this table has a preference for red, as shown by the past. And if you only use the data of the past, this is what you then call hindsight bias, or predicting the past, or retrodiction. Then you will say you're going to bet on red. And that is called that is a bias, but you also have the opposite bias actually. That is called the gambler's fallacy. That says like, well, if it's now so many times red, then it's going to be black because I expect the table to be 50-50. So you can already see the two extremes of this thing is that if it's 20 times red, are you going to predict red? That is empirical forecasting, or are you going to predict black? Because that is the gambler's fallacy. So the two of them, of course, are wrong because we know, well, if we use the physics laws, we know that the table, if it has not been rigged, that it would be 50-50. And that would be then the real Aristotelian idea. Or actually, the real Aristotelian is, if you knew exactly the speed of the roulette table and you know the conditions, you know the temperature, you know all the air molecules, you would be actually able to calculate if it's going to be red or black. And only one of them, either red or black, has 100% probability. So the entire idea of empirical forecasting, it came from about 1693, so you can really pinpoint where it came from Mr. Edmund Halley. He published the death tables of Breslau, that is now called Wrocław, by the way, it's now in Poland. And then without looking at why people died and how they died and things like this, he just did the calculation statistics and then says, like, based on these tables of how people are dying and when they are dying and at what age, I can calculate how much I can have to give them. Imagine they put 1,000 euros in a jar. How much can they take out every year until their death? So this is an entire new, science was born, and that is called actuary, and that is the mother of empirical forecasting, and also actually what made my own university, the University of Amsterdam, famous, because they are the sort of like a center of actuary. Okay, so by looking at the past data, probabilities are determined and the future is planned. So that is the economical implementation or use of empirical forecasting. We also have, for instance, in physics, for instance, for the climate, you have a modern variant of this. That is of this empirical approach. Is you divide the entire the atmosphere in millions of finite element, sort of like small cells, and they are based on very laws of, still with laws of physics behind it, but still there are so many parameters in there that you can adjust, and you will adjust them to the past data. So it basically boils down to, again, doing empirical forecasting. And these kind of things in the climate, they and other areas, they have some problems. And I will list here a couple of them. For instance, the first one is that the underlying laws may be incorrect. Maybe you should first study physics before you apply your physics laws to the finite elements analysis of your atmosphere. They may not be applicable to the system under study. For instance, there are people that are doing the statistical laws and apply them to financial markets, and that may not be correct. The problem can also be it's not clear if the only set of laws that are applicable or if they are sufficient. It can also be that you do not know your boundary conditions. Even if the laws are correct, your input data can be not well considered. And it's not clear if this reductionist approach of reducing it into small interacting cells, it can be done actually at all. Yes, and then after successfully describing predicting the past data, the empirical models might not work for the future data. And this is actually something very a problem. Imagine this has really happened. This is an example that there was a problem of obesity in society. They found out a correlation that there is people that are on average fat, they get a risk. Obesity is a health risk. But don't forget that at the moment we are still having a very young population, and for young people obesity may be a problem, but for old people it's actually the opposite. It is that people are under fat and they are weak, and they can be dying from lack of food. So that can be that actually predicting the past, predicting the actual society at the moment, obesity might be a problem, but in fact it isn't. It can be exactly the opposite. And then the final one, this is also here something that imagine now that you have made in this finite element simulation, you have made a very complicated computer model, and then afterwards you found out that you can predict all your past data, but now the problem is, do you understand your program? So and then you have to study your program. So this I call this the Douglas Adams effect from his book The Hitchhiker's Guide to the Galaxy. They built a super computer, and they had to wait centuries for the calculation what is the meaning of life, and he gave the answer 42. And then they had to build an even bigger computer to analyze actually what was the question that we asked. To give an example, how in extreme, how ridiculous the idea is that the fact that you can simulate the past, that this is then often used as proof of then my model must be correct. Well, look at this. Imagine we have a series in time called let's say this vector 3, 5, 8, 3, 4, etc. And now I write a computer program then saying that if I equals 1, then x equals 3. Else if I equals 2, then x equals 5. Obviously, this completely represents my past data, but it is 100% correct, but it has no underlying knowledge in my computer program. But anyway, I will add here another line saying else if I equals 101, so that will be my tomorrow's data that I predict, and I say x equals 200. Then they will say like, well, my program is correct, so tomorrow it's going to be 200, for sure, because I predicted so well the data from last year's, so this year for sure it's going to be 200. I hope you understand that this is nonsense, but this is basically what they're doing in a lot of this climate research. They don't understand their own program, but the program that they have predicts something, and then they have full faith in their computer program. This, philosophically, the empirical approach is a form of pure inductivism, which has been rejected as a correct approach since it is only applicable to past data and never to the future. To give another example, this is written in Chalmers 1982 in his great book about science. If you have seen, to give another example, if you have seen only lemons in your life, you'll conclude that all citrus fruit are yellow. And then one day you will travel around and you will find that there's also actually oranges, which are of course the color orange. And this is what Mr. Nassim Taleb calls the black swan, because they were having a very nice model explanation, because that's what they do. Then they invent an ad hoc explanation, physical law, why the citrus fruit should be yellow, or why in this case the swans should be white, because they only observed white swans, so they then make a model to predict the past that the swans should all be white. But in fact then they traveled and they found a black swan that undermines your entire theory. Is what Mr. Taleb in his book The Black Swan is actually explaining much nicer than I can do here. The thing is now, in the meantime, you think like, well, if it is all nonsense, then why so many people are doing it? Well, at least we are sort of like reducing all the data. We're making some kind of hypothesis. We can build hypotheses that can be tested. But don't rely on that it is 100% correct. Always be very skeptical. But it's better than doing nothing, of course. In the meantime, we should develop real good theories and constantly test them with incoming data. But don't trust it that only that because you can predict the past, that your model therefore is true. That is probably the biggest error that is being made. That the fact that the simulations can predict the past does not mean anything in itself. This you should then keep at least as a sentence from my presentation here today. Now a little bit about the bell curve, about one of the probability functions, and then later I will talk about other probability functions. But here I will talk now specifically only about the bell curve, which is being used, because where does this bell curve or the normal distribution or the Gaussian curve, these are all synonyms, where does it come from? Well, basically it was if you throw an infinite number of coins, then this is the fraction of heads in coin tosses. So you get the probability density function, by the way. It's not a probability function, but probability density. It comes from this coin flip thingies. And then they will use this bell curve for anything. So basically doing as if nature is constantly throwing coins, flipping coins. While Mr. Einstein already said that God doesn't throw dice. So make here constantly, empirical forecasting is constantly making the assumption that nature is probabilistic. And this is another very big assumption that nobody ever managed to justify. I think I have it here written somewhere that the experimental people think that it has been proven theoretically, and the theoretical people think that it comes from experiment. And both of them, of course, are wrong. It is called deluded by the simplicity of the bell curve, and that is because the bell curve itself is very nice, docile. You can integrate it. You can make all kinds of intervals or whatever, and it looks, in most cases, it looks quite adequate to your real data. But then it will get some quite difficult problems. To get now, let's talk a little bit about the climate. So what is the definition actually of climate? To show why they also use this bell curve, let's talk a little bit about the climate. What is climate? Well, climate is defined as the 30-year unweighted average of the weather. So let's say the climate is the past 30 years. But to keep it in memory in your head, is Mark Twain said this: climate is what you expect, weather is what you get. So combine these two, and then you will see exactly that this is empirical forecasting, because the climate is the 30-year average, so the 30-year past, and with that you start to predict the weather for tomorrow. So climate is what you expect, what you predict based on the past. You predict what is going to be the weather for tomorrow. Thus, climate is the average of the past, prediction for the weather of the future. And for that, very often, they use sort of like then this probability functions. To give you an example here, this is what actually came directly out of the IPCC 2007 report. I didn't repeat the data, otherwise they will sue me for copyright. So I invented something from Gulliver's Travels, so I just made a simulation. This is the winter temperatures from Laputa. The country of Gulliver's Travels. Now, this would be the distribution. You see here these lines. This is what was observed, and then there's some kind of bell curve fitted to it. And then actually we will see that this is going to be it's going to get weirder and weirder. I will show in a moment. But now imagine that in 2004 suddenly we have this line here, which should not be realistically possible. The probability of this is so small. What is it? It's 5.4 sigma outside the bell curve, and it has a probability of 0.00033%. That is basically zero. This should not be possible. And therefore, what did they do it? The exceptional data point is a sign. They say that this is a sign of climate change. Now let's look again. What do we call here? This bell curve, let's say, it has two parameters, which is mu, which is the average, and it has sigma, which is the width of the spread of this curve. So we could say that mu is the climate, which is the prediction of the temperature for tomorrow. That would be here the average of this curve. But we also know that there is variability on top of this climate, and that would be then the weather variations. So if they say that an exceptional point is a sign of climate change, what they're saying is that mu of this thing has changed. That this mu, and maybe also it's getting more extremes or something like this. So what they're going to do, that this data, the experimental data, is forced, and this is very important, is forced into a certain distribution, Gaussian in this case. And if the data is not confirming, like this one, is not confirming realistically to this distribution, we call it an outlier. And what do they do then? They will say that climate has changed, that mu has changed. But nobody will say that the assumption that the Gaussian probability distribution is wrong in the first place. Nobody will say that. While, even if you're going to say that climate has changed, then this point, imagine that this curve has shifted a little bit to the right, but it would be not much, it will not be here, but it will be maybe shifted a little bit, and it will still be an outlier. So immediately if you said that the climate has changed, you still have to reject again this entire analysis. You again have to reject your parameters that you find here. Yes, so the same data point should be used immediately to reject this new hypothesis. Any Gaussian distribution function used will make that there are data points that should not have occurred for the distribution. So actually you should reject this entire Gaussian distribution. So you should reject, actually, if you reject this Gaussian bell curve distribution thingy, you basically reject that there is something such a thing as the climate. There is not such a thing as climate and weather. It is just the things are what they are. And the only real distribution function that you can use for the past, for this data, is the one that predicts the data. So now look again at this function. This is your prediction function, the bell curve, and this is your reality. And this reality is a sum of, and so how much is it? 30 years? Yes, I think 30 of this, which is called the delta functions. So these delta functions are everywhere 0 except in one point where they're infinite, and then the integral of this function is would be 1. Now, and that means that the difference between your function and the reality, this let's say barcode, this is infinitely wrong in an infinite number of places, because where it is here, for instance, it is non-infinite where it should be infinite. And here, for instance, here, it should be 0 and it is non-zero. So it's infinitely wrong in an infinite number of places. So your entire bell curve cannot predict the past in any sort of form. The bell curve is infinitely wrong in an infinite number of places. This leads to strange results. Imagine that we have 3 observations, 10 degrees, 10.0 degrees, 10.2 degrees, and 10.3 degrees. It means that tomorrow 10.1 degrees cannot occur, because 10.1 degrees is not 10.0, 10.2, and 10.3. It never happened. 10.1 never happened, so it can never happen in the future as well. We have abandoned the bell curve, and we now said we can only use delta functions, and therefore 10.1 can never occur. Only that what happened had the probability of happening. All the other possibilities were not possible, as shown by the past data. So this probability, we should not use this probability function, but this probability function of delta functions, because that is the past. And we want to use only past data to make a prediction of the past. And to predict the past data best, we should use a sum of delta functions. Now, the problem is, because the better the past can be predicted, the better is the model, and the best is a sum of delta functions. Now, the error that we made here actually is that we assumed probabilities. And this is the biggest error. We assumed that the nature is working with probabilities. But eventually nature are the result of dependent processes governed by rigorous physical laws. Maybe we don't know them yet, but they are, the laws exist, making the outcome deterministic and nothing like Gaussian at all. Reality is a delta function distribution, what happens with 100% certainty. It happened with 100% certainty, and tomorrow also the things will happen with 100% certainty. Only that what will happen can happen, as Mr. Aristotle, the greatest philosopher ever, actually what he said. Climate change. This is important to remember, that the difference between assuming that it's probabilistic or not probabilistic. Climate change is any data point that moves into the moving average function mentioned above that is not equal to the value of the data point moving out, and therefore saying that the climate has changed when you get new data, that is saying that the climate has changed because the climate has changed. There is no information at all in there, and also you cannot make any prediction on the future about what the climate will do based on what the climate did, by sheer definition of the this entire idea of the definition of the climate and definition of retrodiction and the definition here of empirical forecasting. Another example is how insurance companies, they say that imagine that you're a person X and you have a certain probability to get an accident. Well, what happens if you get an accident? Actually, they adjust your probability function, saying that, well, apparently you had an accident, therefore you must be an accidental person, accident-prone person, as shown by past events. But this accident, of course, was accidental. Maybe your distribution function did not. If you want to, if there are distribution functions, this is actually not at all caused by. It didn't change or at all. But this is just, well, you have an accident. That is actually, it has a probability. There's no need for adjusting the data. And even worse is what they're doing, and in this way they just let you pay by adjusting the value of your policy. That you sign, you're basically paying for your own accident in a let's say delayed after the accident happened. So there is no risk whatsoever for the insurer. So I would not call it actually insuring. I would call it a swindle. Now the other thing is also that they use, for instance, that like me, Caucasian male has a higher risk of getting a car accident. Well, how do they know this? And therefore they will increase my the money they take from me. And how do they know this? Guess what? Exactly on past data that Caucasian males had more accident on average. So there you go. Again, this is an entire actuary, which, as I show here, hopefully doesn't make any sense. To show it in another way, I'm actually repeating a little bit myself, but maybe to make myself very well clear. Imagine. Now, to show it in this way instead of the climate, imagine we roll a 6-phase die. We roll it 1,000 times, and then we say like, well, it seems to be okay. Well, how do we know it seems to be okay? Because we compare it to our physics model, and we see, well, this die is symmetric. It has 6 energy minima that are, so each one of them, we don't see the difference, therefore they must occur equally frequent. So thus we have a non-empirical model, and we see that, well, we cannot throw away this non-empirical model based on our die throw. But now let's assume that we abandon our non-empirical model at all. We do only past data. We only do empirical forecasting. And we see that, well, we started with 161616 maybe, or something like this. But now we roll the die 3 times and we get, what is it, 1, 6, and 4. Now let's look at the last 2. The penultimate throw had probabilities, look at this, it had probabilities of 0, 0, 0, 0, 1. Only 6 had probability of being thrown because it was thrown. Therefore, this has probability. And the last roll was 4, so it had probability 0, 0, 0, 1, 0, 0, because it happened. Now, the final outcome is 4, so the best model is the one that retroactively predicts a 4. both completely, if we do it empirically, we should have predicted 4, and we predict 4 for the past. But also actually, and this is the funny thing, had we done it physically, because nature is completely deterministic, therefore, also if we had used it very well physically, maybe we cannot do it, but had we done it very wisely, we would also have predicted 4 based on physics models. If we knew all the temperature in the room, all the molecules or whatever, so both physically and empirically, we should have wound up with this probability. Once again, Aristotle, this is physical, and empirical also 4. Now, for the future, the high probability, an empirical model will say that the next throw has high probability of 4, because it happens in the past. An educated guess model will continue saying 1/6 for all numbers, because that is our, because of symmetry reasons, some kind of mathematics, and we think that nature is chaotic and actually uses probabilities. While it doesn't, but we think so. Well, if we use real analysis, we would have to know 100% probability for a certain number that we don't know because we are ignorant and we don't know the starting conditions and so on. Now, so in other words, the probability to analyze the weather events like die rolls and events and card shuffles are completely deterministic. We are only blinded by our own ignorance. So the more ignorant we are, the more we talk in probabilities. The fact that we cannot determine the physical laws of the system and calculate the outcomes doesn't make that the physical laws don't exist and that it should not be possible to calculate. But we cannot calculate. It doesn't make it non-deterministic if we cannot determine it. Nature is deterministic, governed by the laws of thermodynamics, and only looks random to us. But they use retrodiction, empirical forecasting, puts everything in probabilities, and the distribution parameters, the parameters of the distribution functions are determined from past data. Now, this distribution functions then has one very important limitation. It has to be of the probability type, meaning it should be able to integrate it, and the integration should be yield unity, meaning 100%, because something should happen. This limitation, that while, as we have just argued above, nature is deterministic, so it doesn't need probability functions. So this limitation of functions is thus ungrounded. It is trying to force nature into non-deterministic idea through probability functions, because we, stupid humans, can only work with it like that because we don't know the laws of physics and we don't know all the parameters and all the starting conditions. But okay, let's for the moment use the standard tactics of modeling the past data with docile probability functions. Climate is the 30-point average of the weather, remember? Now let's analyze this with the event that happened in Pakistan some time ago. There was never a flooding in Pakistan in 99 years, and suddenly there's a flooding in Pakistan. So what happened? The probability of flooding was 0%, as shown by the fact that it didn't happen in 99 years, so that's already more than 3 climate points. The probability is 0. Our prediction was 0, but last year the probability was 1 because it happened. Now, what will be the probability of having a flooding in Pakistan next year? Well, from our definition, the probability of flooding for the coming years is 3.3% per year. Namely, it happened once in the 30-year climate window. That is strange, because now the probability of a flood depends on our quite arbitrary definition of climate. Namely, the probability is 1 divided by n, with n the number of years in our climate window. So if I define climate as 50 years, then I would have a probability of 2% next year. And if the probability is the number climate is 30 years, I get 3.3% probability of flooding next year. Well, nobody can explain me why it should be 30 years and not 50 years, or not 100 or 1,000. This is just coming complete out of the air, but it determines my prediction for the flooding in next year in Pakistan. That is the outcome of the empirical approach. So you see that it is another pitfall or a peril. Imagine we do this with a die roll. If the probabilities of the die were purely empirically determined by the last 30 rolls. Now, we know it from symmetry how it goes, but Therefore, we ignore this 30-roll statistics and we stick to our non-empirical probabilities. That is because we know how the die roll works quite well, because it's a simple system. Now for the climate we don't know how it works, and then we say we go to do it in a statistical way. So the more stupid we are, the more we use stupid tools like empirical forecasting. That is also called chaos theory. Chaos theory is like the weather is chaotic, is the idea that nature is deterministic but too complex for humans to understand it. It is pseudo-random, it looks like random to us, and we model it by random events. So I'm now about halfway. Well, the second part will be a little bit shorter. I talked to you here about what are the problems of empirical forecasting, and it has got to do with that the nature is not probabilistic, nature is deterministic, as Mr. Aristotle said, and therefore any analysis based on probabilities are nonsense. And then also using probability functions is absolutely not a good idea. And on top of that, the fact that you use the Gauss curve or the bell curve or the normal distribution, that is just because you are finding the nice simple and you know how to work with that. So this is what they say, if you have a hammer as a tool, all problems look like nails. So you use the Gauss curve because this is the one that you know how to work with, and you apply it to anything. In the second part I will show to you more specifically about this the function and what is the problem with that in a little bit more detail. So see you in the next video.